Okay, so this video is self-documentation for how I built this Serge-style synthesizer. Maybe other people will also find it interesting. So what is a Serge synthesizer? So here's a Wikipedia page. So this format was developed in the 70s by Serge Trepnin. And if you want to know more about the history, you can read this or find videos on YouTube. But if you're familiar with Eurorack modular, it's very similar, except that it uses banana jacks, so 4mm single conductor jacks. And then also the voltage range is slightly different. Basically, it uses 5 volt instead of 10 volt peak to peak. So there's that. So if you want to mess around with Serge, then you have a couple of choices. So you can buy pre-built systems. So Serge is in business at this moment in time. Disappeared for a while and came back. So the kind of classic way to get into Serge is to buy a panel. So let's see if this page will load up and we can see some panels. So here's an example panel for vintage Serge sold by Serge Modular. So you can just go buy one of these. There are also pre-built systems available from other, I guess I'll call them brands, but people who followed Serge. So there's some differences maybe in some of the circuits and so forth. So low gain is one. You can buy complete pre-built panels from low gain. Prism is another. There is loudest warning, where you can talk to them and get a custom built panel, maybe exactly what you want. And then you can buy full panels from elby in Australia. These are the major ones. I'm sure there are others. In addition to this, over the last, I don't know, decade or something, there has been a shift to creating like modules. So instead of a full panel, just a single module with its own faceplate, right? And then in the classic Eurorack fashion, you can mix and match these. Serge even offers a Eurorack size and Eurorack format version of these modules, obviously with the different jacks and stuff. You can also get those kinds of modules from Logain. So let me back up here and show you one. So here's one from Logain. Click on it. Right, so it looks very much like a Eurorack module. And likewise with Prism. Now, you can get these pre-built. So Logain offers them pre-built. I'm pretty sure Prism also offers them pre-built. I don't know if you can buy individual individual modules from Loudest Warning. I don't know either if you can buy them individual things pre-built from elby. I don't think you can. I think elby is only panels. So let me show you something else that's kind of interesting about these newer approaches to Serge, and that is the way that they're built. So I believe now Serge and Logain and Prism by default will build their panels and their modules like this. So you'll have I kind of wish it didn't zoom in here, but let's go with it. So you'll have like an aluminum plate, that's the front panel. And behind that, you'll have an I/O board that the front panel components connect to. And then there'll be an actual logic signal processing board behind that. And notice that the boards are parallel to each other. And that makes sense because it all needs to fit behind this, base plate. You could have them be perpendicular, and in fact, you'll see that approach sometimes being perpendicular. However, the traditional way to create these panels is to have what's called flywire. And in that approach, your front panel components will be connected by long wires. So like here at the banana jack terminal, you might have a wire of several inches that goes to a board. So those designs omit this IO board, I'll call it an IO board, that disappears, and instead you have these wires go. Now, the flywire approach is much more labor intensive. Um, like it's so much more labor intensive. But one thing that's kind of interesting about it is that it gives you a kind of flexibility to surface the module functionality that you want to surface. So for example, if I'm um, buying this particular module, it's already pre-drilled and everything, and it really only makes sense to use all of the jacks and controls and stuff that it's drilled for. But you can approach this in a more kind of custom way where there's flexibility. And in Surge, the typical way to do that is to do a paper. Okay, let's go back up here. Use a paper face approach. And so with this, you might have a panel. I think the original ones were pre-drilled with holes. And then you would just cover the whole thing with paper, and then the holes that you weren't using, they would be covered with paper, right? And the holes that you were using, you'd put a hole there and you'd put your component there, right? So you'd have this kind of Swiss cheese board where everything that you weren't using, that was covered up. Um, and there's like various instantiations of this. So I think this is like a sheet of aluminum here, and it's marked, and you would probably drill it, I guess, because that's what this is doing. So yeah, so the only reason I think to use flywire connections is if you want to do something where the actual interface of the module is not standard, right? Um, and that's what I did, and I'll be showing you some of that later. So if we come over here to elby, yeah, I'll show you this on a different page. So as far as getting any of these modules pre-built or kits, besides the manufacturers, you can also get stuff from Modular Addict. They also sell supplies and banana cables and stuff. And then SynthCube also sells stuff. Yeah. All right, so let me kind of switch back here. So let me explain the LB website a little bit because it's quite interesting. So if you go to the LB website and dig around, probably the first thing you would encounter is a page like this where you'll see a product to buy. And when you go to the drop down, you can see you can buy a PCB or you can buy component kits, and I'll explain what those are later. But if you don't know what this does, like what a smooth and step generator does, it's kind of like not present on this page. You have to go like click this link here, right? Let me just go back to that. And that takes you to a page like this, right? And then you would do that for maybe every module that you're interested in. Alternatively, there's this page, which has a listing of all of the CGS, and I think the Surge module is also on this page, and you see a little description of each one, and then these link out to the build page that I showed here. So there's multiple ways to get to this page, but I think as a kind of overall index, this particular page is pretty useful, and it's kind of hard to find, I think. Okay, so let's say that you're on this build page, and you want to find out about it. You can read all this. In the previous version here, you can keep clicking on that through all the versions, and eventually you'll bottom out on the original Kinstone CGS page. And these have circuit diagrams, which are really, really useful. Sometimes there's other information that's useful as well. So even though the LB current page often does not have a circuit diagram, you can hit the previous version link and get to one. All right, so let's scroll down here. And then at the bottom of the page, you've got the build guide. All right, so I think I'll go ahead and click on that. So on the build guide, you'll have this page, and you'll have an overlay that shows the silk screen with no components, the plan view, which shows the components, and a 3D model view, which I personally don't find that useful. And then there will also be a PCB bill of materials. So this is the bill of materials. And you can see like each component and how many you need, and their names on the silk screen and the package, right? So it's the back. And there might be some like notes of changes, things that you might do differently. This may or may not be present. Let's go to panel wiring. So panel wiring shows you how to wire the PCB to the front panel components. And as you can see, they're just directly wired, right? And these wires are shown like as an inch length, but they can be much longer than that. You have to be really careful looking at these because sometimes these are upside down and sometimes the pots are shown from the back and sometimes they're shown from the front. So you just have to be really careful looking at these. But on this page, there's a hardware bill of materials. So if we click on that, we can see all the materials for the front panel components, right? So for each module, you're going to have two different bills of materials, one for the front panel components and one for the PCB components. And sometimes things that you might think belong on one might be on the other. And I guess the logic for how this is divided up is whether or not there's a fly wire between them or something. Sometimes you might see like wire link or something, and you would think it belongs somewhere else. Okay, so then if the module requires calibration, there's a calibration page that will have the procedure. So, you know, it's kind of like all the information is there, but you kind of have to dig through it a little bit to get everything. There are other pages as well that are important. So one is this FAQ page. And the FAQ page just has kind of an overview, but one of the things that's most useful in it, I think, is this, where it just gives the general values and tolerances of components. So like all resistors are 1%. Here it says half watt, but I use quarter watt pretty much everywhere and it's fine. You know, it talks about what pots they use. This one's pretty useful. If it's less than a nanofarad, it's some sort of, you know, temperature compensated ceramic or 2.5% polystyrene, blah, blah, blah. So, you know, some of that's useful to know what kind of component you need when it's not really specifically, not specified in a detailed way on the bills of materials. Another useful page is this one, which is really for their panel kits. Because in it, they have a lot of the color conventions for the wires and so forth. So like blue being -12, 0 volts, red being +12. But when you're looking at the wiring diagrams for a module, all these color conventions are used and they're not, I don't know, I don't feel like they're explained anywhere else, but maybe they are and I just didn't see it. But like, for example, you often see this brown, red, orange convention for potentiometers and so forth. So it's kind of useful for that. And then there's a whole series of pages that talk about components that are used across all modules. Yeah, across all modules. And a lot of it's very standard information, but some of it isn't, so you kind of have to read through all of it. At least I would recommend you do that. Okay, so yeah, okay, so I'm going to switch to bill of materials. So what I did is, you might have noticed when I tried to highlight one of these, it doesn't like copy paste very well as a spreadsheet. So I actually used AI to combine all these bills of materials for all the modules I wanted to do into this spreadsheet. And then to be more specific, I took the PDF, sent it through a large language model, and it gave me comma separated values, which I pasted into the spreadsheet. And one thing I would suggest is that if you have multiple modules, it's probably better, multiple of the same module, it's probably better just to duplicate these entries so you don't have to multiply things out later. So I did that and I checked it. And then let me see. I think we can just skip over to this. Let me back out a little bit. I'm going to do this. So then I made a pivot table of that bill of materials, and that gave me a count of each part across all of my modules. So you can see here, here's a 100K resistor. I need 137 of those, right? I'm getting it from Tata, so I got a lot of my parts from Tata because they're the cheapest as far as I could tell. Tata sells that resistor in packs of 10, so I needed 14 packs to get my total amount, right? Here's the Tata SKU. So it's really useful, I think, as you go through and build one of these, have the link back to the website for that part, but then also have the identifier, SKU, whatever, for the part, because most of these sites have shopping cart builders where you can just paste in like the SKU, how many you need, and it will assemble a shopping cart for you, so you don't have to click on these links all over again. I made a lot of substitutions, uh, going for, in many cases, the cheapest part that had the right tolerances. So here's a great example. So you can see here with these capacitors from like here to here, they'll have the same Tata SKU. I guess that, yeah, it's going to go off screen. They'll have the same Tata SKU. Oops, great. They'll have the same Tata SKU. And in this case, you can see that, there we go, that the 100 NF, I just used Mylar. So that worked out pretty well for me. I'll talk about some of the places where it's maybe not so great. But yeah, so I used like the cheapest components I could find off of Tata. Everything works, but I'll give you some caveats later. Wherever Tata did not sell something with the tolerances I needed, I would buy multiple of that thing, and then I would basically like hand match to get the tolerances I needed. So, you know, if I needed this and they only had 10%, I'd buy twice as many, and then I would match it out myself. Every once in a while, you'll see I have a thing here where I made an error. In this case, I thought it was 100 NF, where I should have had 100 PF, so I had to go back later and buy that somewhere else. Okay, so most of the stuff is pretty straightforward. I used quarter watt resistors throughout, not a problem. What I couldn't buy from Tata, I mostly bought from Mouser. There are a couple of things in here that are worth talking about. But yeah, polystyrene and stuff. I didn't buy any. Yeah, I don't think I bought anything that was polystyrene. So like a lot of these things I might have used like, what does that even say? Polypropylene. Yeah, I used polypropylene instead of polystyrene. You scroll down here. So some of the stuff that's kind of interesting. Here we go. So some of these banana jack sockets, I originally thought that I would use the Tata brand sockets, and I bought those. They were like 9 cents each or something. I just didn't like those. They were just a little bit too flimsy for me. So I actually ended up finding some that were like surplus from Indigo Instruments. I got those for 30 cents each, so they cost 3 times as much as Tata. But these are cinch jacks, and like $1 is a good price on Mouser. So I feel pretty good about that. I could only get them in black though. Some other things I got from Tata, I got these banana plugs. They're working out pretty well. So I use these to make my own cables. I also bought Davies knobs with brass inserts. I thought this was a pretty good deal. You could only get black or white though from Tata, but that's fine. And then I bought like a bunch of switches and stuff I won't even show you. And a lot of pots and stuff from Tata, and that's all fine. The pots are a little bit stiff, but I'm sure they'll work themselves out as we go. Um, some of these things, like I had to do kind of weird substitutions. So like here's some JFETs. So for the JFETs, Tata only had SMT. Should stop doing that. Only had SMT, so I would buy that and then get an adapter. I did some research and I think I worked out that that was cheaper. Otherwise, I wouldn't have done it. It was cheaper than trying to find that as a through hole because some of these parts are really old and the original through hole parts are hard to find. So there, it was pretty common for me to do stuff with adapters, and I'll show you some examples of that. I think the final thing, two final things I'll talk about on this is matched transistors. So a lot of these designs require um, matched transistors, and elby's got a page about this that's pretty useful. And it talks about like, here's an integrated circuit you can get that has the matched transistors on it. But when you go and you look for these, they're pretty expensive. So like, here's, I don't know if I've got this somewhere. Yeah, so like here's a LS358. It was 550 at LB for one IC, and that was actually a pretty good price. But if you want to, you can actually hand match your own transistors, and that's what I ended up doing. So everything you see here, you can get from some combination of 847s and 857s. So I used the Yatma transistor matcher circuit to hand match everything. And I would buy like twice as many transistors or three times as many transistors as I needed. And then I would just hand match them to find matched pairs. And by doing that, I saved a lot of money, but it took a lot of time. Well, maybe I should say I saved some money, but it took a lot of time. Because the transistors I used cost like 4 cents. So 4 cents versus $5. You can kind of get a sense of what it's like. And then I would thermally bond the match transistors with epoxy and stuff. Another thing I did was Timcos. I use SMT Timcos. So Timcos get really expensive. One of these Timcos was $13 at LB for, I think, for just one. But you can buy SMT Timcos from Mouser. I think I got them for 50 cents. And so what I did was I just used these ppm values were close enough. I just used I got a bunch some 1Ks, and when I needed a 2K, I just put 1Ks together. You can also do stuff to adjust for like the ppm value by adding an inline resistor, but there's not necessarily PCB space for that. So yeah, I mean, my temperature drift compensation is probably not as good as if I had bought the 100% correct thing, but it's better than nothing, I think, and it seems to be working out fine. So I'll show you some pictures of how I did that. Got this additional mods. Yeah, I ended up buying some wire that I didn't use because I realized that I needed to use silicone wire. So I very strongly recommend silicone wire for this stuff. It's just has the flexibility needed for fly wire stuff like what I did. 7 colors was fine. That let me match LB's color scheme with very few substitutions. I used 24 gauge for that. I used 20 gauge for power. I actually ended up buying 6 colors. I wish I had only bought 3. I thought I could use the extra colors in case I ran out of 24 gauge, which I did. I had to buy ended up with 60 feet of 24 gauge. But this was too big for front panel components, and it wasn't as flexible, I think, because of the increased gauge. For doing the power, this worked fine with the larger crimp connectors, the 3.96, but for the 254, it was hard to crimp this. So I would not go larger, especially if you're using 254 crimp. It's just very hard to work with. Okay, so going back to additional mods, I bought a strip board to make pot adapters. I'll show you that. Made my own format jumbler, bought some parts for that. bought silicone test lead. It's actually really high quality Pomona to make my banana cables. So I got enough test lead and enough plugs to make 100 banana cables for $100, which I thought was pretty good. And then I'm using 4MS Row Power 35 for power because it's got a spot to solder on MTA header. And so I'm just running off of that, and that seems fine. Doing that because I previously already worked out how to run this off a chainsaw battery. So I just figured I'd stay with it. And I've got a couple different modification things in here. I don't even know if I remember all of them. A few of them I did get from Loudest Warning. If you go to Loudest Warning and you click on some of these, you'll get like his notes about things. And there's some nuggets in there for sure. Okay, so going back. So I think that's, oh, and so one other thing I did, which is kind of useful, is I made an inverted index, and basically this just reformats the previous spreadsheet so that for a given component, I know what modules it's used in. And that just made it kind of easy to find things across across modules. And I'll show you my organization system next, I guess. All right, so this is the initial kind of panel design I started off with. This was just done in PowerPoint. I actually used the Paperface template from Logain just to position things. And I just copy pasted out like elby's artwork onto it. So this stuff right here. So it was just to give me an idea of what I could fit on a panel, some like general layout, and I revised this a couple of times. Once I put my data order, so sorry, this is actually the CGS. So once I put in my order with elby for the PCBs, I assigned each one a letter, a sticky letter, and I created a box of bags. So there was a bag for each module where I put the letter and then also the CGS number on it. And in that bag went all of the specific components to that module that were not shared by any other modules. Also, the PCB went in there, you know, with anti-static bags and silica gel and stuff like that. Any component that was in the majority of modules, like 100K resistors and stuff like that, I put in a universal bag. And any other component that was in multiple modules went in a big bag where I put a sticky letter on it for each module. So when I needed to build a module, I would go to this bag first. I would very quickly sort through it and grab anything that had the right letter on it, which was extremely fast to do. You know, just took like 1 or 2 minutes. I would grab the entire universal bag and I would grab the bag that was specific to that module. And it worked out pretty well, and it let me keep all the components in their original bags instead of trying to break out things into many little bags where I would have lost the kind of traceability of the original label. So here's some pictures of stuff. There's some cases. I ended up not using that case. I'll talk about it later. This is the hand matching that I did. I used this Yatma board that I got off someone on ModWiggler. I had a mistake in some of the components, so it was a little bit glitchy at first, but this far right is what it looked like when it was working, and it let me match things like super, super, super closely. Okay, so the rest of the stuff is just builds for a little bit. If you want to skip ahead, just shows some examples of some of the matching of components or substitutions of components I did. So this is SMT converted to through hole for the JFETs. This is me dealing with some oversized resistors because Tata, I don't even remember what these were, if they were like 1 watt or half watt, they were giant. I ended up putting those in a different way later where they stand off the board more. You can kind of get a sense for, you know, when I use these giant Mylar capacitors, there were situations where I had to do a little bit of bending to get things to fit. I always managed to make it fit though, so it's totally possible to do it this way if you want to. Here's where I started doing something a little bit smarter with large resistors, I kind of made a triangle. And that made it easier for it to fit in the footprint by going a little bit vertical. Um, building stuff. Triple wave shapers, boring. Okay, stereo mix. So this is the first place that I got a bit by choosing components that had the right electrical specifications, but were mechanically like not correct. So like the wrong size. And you can see that here. So these boards touching my hand, these are channel boards, and in the normal LB build, this is flipped up. And so I had to flip it the way that I did because there wasn't space to flip up. Like this resistor, sorry, this capacitor would hit that capacitor, right? You also have to think about in uh, these things, what's the orientation of um, the trimmers, so that you can actually get a screwdriver in there to turn the screw when you're calibrating, which would have been hard for me because these trimmers have the screw come out and they really should be touching my hand, I think, in the original specification. So I had to mess around with this a little bit to get it to work. You can see here, I had some other problems. So this is the output board that stacks on the main board. And basically any place where I had board stack, I had to solve for a connection. So this is the standard approach that I used. These are header pins. And you can see like here's female, male, and then female. And the way that I made this work is that I would take the male and I would center the pin so there was an equal amount above and below. And it's basically floating here and holding the two females together. And it makes a good enough connection. But that's how I got the height. And then I also had to buy some spacers that match that height. Here, because the whole thing was so wobbly, I ended up epoxying the spacers onto the board. I actually like shifted the spacer over to the right because you can see there's a hole here that I wasn't able to use because of the capacitor. But actually all worked out fine. This was like one of the only places where M2.5 screw was specified. Um, and since my spacer was M3, I filled it with hot glue. I basically hot glued a screw into it. So I can unscrew this, the hot glue creates threads. So it's pretty solid. It's fine, but that's just an example of the kind of stuff I had to work around. All right, here's an example with, what is this? The resonant equalizer, same kind of deal. I use the same technique of joining the boards. So, basically anything with a double board, I had to do that with. This one's kind of interesting. This is where I used SMT Timcos. So you can see here my SMT, I don't know if it's 120, was it 1206 package. And what I did was I just took some um, resistor legs and created like a little bracket for the SMT. I actually messed this one up because I should have used two in series on this one, but I wasn't careful with my notes. Here you can see I basically made a space in the dip, whatever you call this, the IC mounting block to allow thermal paste to go through. So here's it in position with thermal paste. Right, and you can see the thermal paste. So the Timco is thermally connected to the chip. And here you'll see this is where I redid it by having two in series. So it's kind of a little bit ugly because I'm cleaning up and redoing something I already done. But again, it worked. Totally fine, no problem. I can't tell if there's a problem. VCA, so here's an example of a matched transistor set where I used epoxy so that they're thermally bonded, or thermally coupled, maybe I should say. This is an example of working with large resistors, having them alternate which side stands proud of the board. Another example of stacking, same deal, same approach. VCOs had a lot of weird substitutions. So this one actually had a spot for a SMT Temco, which was not specified. So you actually had to look at the board to see that. But that was nice. That saved me a little bit of hassle. So it's soldered in. There's some match transistors put over it. Here's a capacitor I had to give wider legs. I think maybe an axial capacitor, maybe polystyrene was specified for this, and I used polypropylene. So I just used strip board. You can actually see there. I used strip board, I soldered it, and then I cut it here after soldering it, just to make it easier to solder. Here's a JFET, right, in this position. So there's a JFET. Here's the crazy capacitor. So definitely ugly, definitely some weird stuff on this. But again, it all works. It sounds great. So these are the two matched transistors coupled with epoxy thermal paste below. So it's thermally coupled to that Timco. And hopefully this won't run out when it gets hot. If you think it will, please leave a comment. And in fact, like leave any comments and I'll put corrections at the top, like pin that to the top of the comments. Okay, I made my own headphone amplifier board using the Outsy design, which you can find online. I use Labor to do that. It's fun. I found these nice little PCB style, well, I don't know, I wouldn't call it a strip board, but PCB style blank boards. Got a really good deal on Amazon. I don't remember if they were like $1 or less each. It was crazy. Missing a jumper wire here. Yeah, so yeah, all throughout you'll see things that maybe there's something missing. Where at the time I might maybe took a picture before I completely finished or noticed it later. Yeah, I cleaned this up later for sure. All right, here's a new layout. This is very close to the final. I guess I'll go ahead and talk about it. So oscillator oscillator here, triple wave shaper, gated comparator where I broke out the DAC so that I can put arbitrary inputs here and get a Voct signal out, wave multiplier, peak and trough, SSG with a noise nested in between, ring mod, gate sequencer, two processors, NCOM, DUSG, sorry, that's not NCOM, VCA, DUSG, NCOM, mixer, VCFQ, VCA, resonant equalizer. These VCAs also double as mixers. I'll explain that a little bit. This is a kind of like a test panel I made to kind of test the art and the lasering. I used a laser to make my panel. I had some revisions after this. You can see the LEDs are interfering with the text. Let's see. And I marked it up just to say, like, this is where, you know, the B50 pots go, and this is the switch that I used. And again, some of these things changed. Probably the most important thing at this time was a fit test. So here are my 16 millimeter pots, and they're obviously way too big. So I had to use, I guess, 9 millimeter pots. I started doing a fit test with my components. This is like a stress fit test. None of this is a real layout. One of the issues I also faced was keeping my laser from blowing through the board for levering. I also did these offset engraves so that the washer is flush with the surface. And I had to do that because the Tata pots did not have enough thread for me to be able to use this white board. So actually, originally, I thought I might use this white board. This is called Eucatyl. It's acrylic bonded to HDF. The HDF is made from eucalyptus, so it's, you know, very environmentally sustainable, I guess I'll say friendly. And I thought this would be really cool, easy way to get a kind of paper face vibe. But unfortunately, it's too thick for the Tata pots, and I could not engrave out the washers to offset the washers because this stuff just kind of chars. Also, it might not have been strong enough. I think it probably would have been, but I ended up using uh, Baltic birch. So this is a fit test from behind. You can see it's fine. You know, there's enough space between things. They're not touching. It's tight in places. Then I started working on the board layout. So I wasn't actually sure how I was going to arrange the boards behind this. I decided not to do it in the computer. I just did everything, uh, using real world mockups. Um, so I tried both parallel and then perpendicular orientations. Perpendicular with one row was too long, so I created a second row, which may be a little bit hard to see here. But basically, there's two rows. There's one row that's close to the board, and then the second row is offset from the first row, and the second row only has 1 inch PCBs. So many of the LB PCBs are 2 inches wide. I think the wave multiplier is 3. And of course, there's ones that are stacked. The ones that are stacked are usually like a 1 stacked with a 2 or something like that. So the maximum depth of PCBs is something like 4 inches here. It's the 3 inches of the wave multiplier plus the 1 inch of the second row. That is a bird's eye view. Okay, good, good, good. All right, so for the finish, I originally thought I would use a gel stain because that works well with birch plywood, but it highlights the pores. The pores are very dark here, and I thought that would interfere with the lettering. So I decided to use a dye like what is used on electric guitars. So I did a bunch of finish tests, which are not going to be super interesting. But basically, I ended up using this red and a kind of complicated process with mixing it into shellac and spraying that. I made a format jumbler. This is acrylic. It's like 2mm acrylic, so it's very bendy. So I reinforced it with some scrap acrylic I had that helped with the flex. It seems to be good enough. And then these are 3-position switches. One position cuts the signal in half using a voltage divider. So that's great from going from 10-volt Euro rack to 5-volt surge. Middle position is a mute, and the final position is nothing. And it seems to be fine. It's all passive. I think I calculated, gosh, what did I calculate the current draw? I can't remember what I calculated the current draw as, but it's pretty low. 2 milliamps maybe. For power, I use these terminal blocks, which I got on Amazon for like 15 bucks with a bunch of connectors, like crimp connectors. So that seemed like a good deal. Did a fit test using HDF. Designed this whole boat and panel. It's integrated using Fusion 360 and then laser cut it. So here you can see, yeah, I'll just talk about this. So here you can see it with the back open. So really everything is accessed through the back panel. And then the way that I connected the PCBs to this is they're actually connected with 2mm bungee cord. So these little fins or ribs have holes in them that the cord goes through. And I thought about using screws, but I wasn't sure I'd be able to get a screwdriver back in there. And one thing that's kind of neat about this cord is that it's a shock absorber. So these boards, they will move slightly when this is taut, but not really. And vibrations are absorbed. So it's kind of cool. And it's not really that hard to tie knots and free knots with this. I use some needle nose pliers, but yeah, I've taken out a single board when this thing is full, and it's, you go slow and everything, but it's totally doable. Probably not as easy as other designs, but yeah, it worked. It was pretty inexpensive. So these just show some fit tests of everything. The mixer turned out to be a problem. You can see here it's touching these front panel components. I only allowed about 1 inch between the back of the front panel and the beginning of the PCBs, like the edge of the PCBs. So I had to reposition the channel boards on the stereo mixer. One I folded over, and one I just reversed the offset, so it was offset in more. And that solved it. That was fine. So this is the second picture. Here's the fit test, fully populated with the terminal blocks. So looking good. Still made some revisions. This is me laser cutting the front panel. which is, I think this is the final design that was used. Um, Here is everything getting ready to finish. So I actually finished this before gluing because I had different sides were going to receive different kinds of finish. So I decided to do it that way. First, I did the front panel. And you can see here the front panel. So this was finished in a multi-step process with some kind of base coats of polyurethane to prevent the wood from absorbing the finish in an uneven way. And then I used trans-tint dye and shellac and sprayed it on. I did this, it was like 30 degrees outside. I had some issues and I didn't scrap it. I knew that there were some defects in this, but I decided just to go with it because I actually at the time had a misunderstanding about some of the safety stuff with trans tint, and I just didn't want to deal with it again. It turns out trans tint is much safer than I thought, and so yeah, but it actually looks really good. You'll see some pictures of it. If you zoom in really close, you'll see some stuff. Some of this is just uh, not necessarily unevenness, but changes in how the light is reflecting off places that received more or less shellac. But anyway, here's a color difference between the two. If I had to do this again, I'd probably not tint the shellac. I'd probably just use a shellac, like garnet shellac, that has a stronger color. Because if I ever need to repair the finish on this, it's gonna be weird because the dye is in the shellac. So if I change the shellac, it'll change the dye. So it'll create some kind of discoloration. So I guess we'll find out if that's a problem or not. This is me gluing the ribs on, the parts that the boards are connected with bungee to. And then this is me spraying on just plain shellac onto everything. Yep, it was like 30 degrees. It's pretty cold. This is my glue setup. I diluted Titebond, I think 5%, whatever the recommended dilution is, and that created a longer working time, closer to 20 minutes, and also let me use a squeeze bottle instead of a brush to apply it. I used these Harbor Freight ratchet clamps to do the corners, and then I forgot. Um, let's see, it's right here. So the back piece, which is the only part of this that is not glued to the rest, I had to incorporate into the glue up in order to distribute pressure correctly. So I actually waxed the inside of this and the teeth to prevent the glue from sticking to it. So if I had made a mistake at this point, it all would have been ruined because this back would have been glued on and I wouldn't have been able to put the modules inside. Fortunately, it turned out fine. You can see the reason why here. So that back piece is on the bottom and these clamps are squeezing on it in order to hold the top and the bottom together. So I needed that back piece on to distribute pressure evenly. So yeah, that was a tense moment. This is the outcome of it. Um, so it looks pretty good. I kicked around the idea of doing something with a boat in terms of color and stuff, but when I first designed this, I never really intended the boat to be seen. Later on, I started to get kind of attached to the side of the boat. So again, if I had to do this all over, I'd just do the whole thing with like garnet shellac, I think. This is what it looks like from the back. As you can see, the back opens for access, putting in components, banana jacks, putting in pots, putting in everything. This is what it looks like from the inside. I got these LED lenses thinking that they would color the light. My LEDs were so bright, they didn't really do anything, but they still served to hold the LEDs in place against the panel. I use hot glue for that. One interesting thing about the hot glue is that when I applied the hot glue and I pushed the lens into it, some of the glue went through the hole and created a light pipe out of hot glue. And that actually is a really cool technique. Um, it took basically I didn't practice this. I just did it like in real time. And it's just not all the light pipes are the same length. But I think it's fine. But yeah, kind of interesting technique to maybe use in the future. I'll tell you how I solved the LED brightness problem in a second. Here's a close up to the panel. You can kind of see here some of the defects or variations, I think, in the color. This is the kind of thing you see if you zoom in. Under regular light, you just can't see it. This is a pot adapter I made out of strip board. I score all the way across and snap across this piece of wood and then clip off 3 at a time using wire snips. I'll show you an example of a completed one in a second. Here are the terminal blocks in place. Power runs to the center of one side. Power runs to the other side, like right next to it. So basically, it's kind of a branching distribution instead of all being like power going in on one end and then all the modules kind of fighting for power as you go along. So maybe slightly better than that. Red is plus 12, blue is 0 volts, and black is minus 12. I could not choose the colors. That just came as it comes. Crimping, use this tool. It's really great. Lots of crimping. Usually I do soldering outside, but it was like 15 degrees outside and we were actually snowed in at one point here. So I took a bathroom fan and hooked up some spare, like in a monitor stand and some spare pipe I had and created a fume extractor with that going out the window, some air conditioner insulation there. That worked really well. So basically at this point, I'm just attaching wires to, or getting wires measured to attach to the boards, attaching those wires to the board, and then attaching wires to the case. So I wanted to try to do this all in one kind of working position, one setup, and it didn't really work very well for me. So I ended up kind of creating like different workstations. So I would clear out this workstation in a different configuration for each task, and that worked much better. So the first thing I would do is I would measure all the wires with the PCB elevated a couple of centimeters off the boat. And this is like service position if I ever need to pull it out and mess with it. This is the position it was calibrated in. I'd measure, cut, and then tin all the wires, label them all as well. So this is what tinning would look like. Tinning each one took a long time. Then I'd attach the wires to the PCB. Using the elby color scheme helped. Use these Velcro ties to have the cables go in the direction that I wanted pretty commonly. Here's an example of the pot adapter boards. So like looking at this lower one, so I have a pot with 3 terminals. I attach the wires to the 3 bottom holes, and then the potentiometer lugs would go in the 3 top holes, right? So they would have a strong mechanical connection and then be electrically connected through the copper strip that's in the strip board, and then also the solder. By the time this was done, these were like a solid strip of solder sitting on top of that copper. Okay, kind of boring, just more stuff. Oh, so this is actually, I would make these cradles out of 2 Velcro straps, and this actually worked out really well since the wires were tinned. They would have a certain amount of friction when they were in the corresponding PCB holes. And then with just like a little bit of support from this cradle, they would mostly stay in place. So I was able, oftentimes, once I got into this method, I might be able to do up like an entire side of the PCB and solder them without any falling out in the process. So this is me soldering. So the board already has the wires connected to it, and I'm soldering the wires into the boat. So all the components are already like fixed in the boat. This is one thing I didn't mention earlier, I forgot. The kind of classic banana jacks, you can't yeah, so once it's like wired in, I mean, I guess yeah, once these banana jacks are wired in, you have kind of an issue where you can't pull them out of the panel. So the pots, you can unscrew the nut on the pot and pull the pot through the backside of the panel, but the bananas, you can't do that unless you buy special bananas that allow it. So that's kind of an interesting way that some of the stuff maybe differs from Euro a little bit. Like in Euro, you can pretty much always remove the front panel just by loosening nuts and stuff off the module. But things are much like more integrated in this style. Okay, yeah, so I guess the only other thing I would say about this is that, sometimes it's kind of interesting and complicated to work in this kind of depth. You just don't have the clearance for soldering. So I very frequently would have like a 4 or 5 inch long piece of solder that I was very, delicately positioning with one hand while I had my iron in my other hand. So it definitely required some thoughtful differences in how I normally work. Here's some examples of those PCB adapters on pots before being soldered. So you can kind of see what that looks like. I thought it looked pretty clean, even though they're a little bit ragged edged. I would solder all this stuff and then clean it. So everything has been cleaned, like all the wire connections to the PCB was cleaned with alcohol and so forth. For calibration, I used a multimeter. I generated test signals with the Mordax data and an oscilloscope. I always checked the Mordax data's signals with the oscilloscope to make sure the data was doing it correctly. And sometimes it wasn't, sometimes it wasn't. Um, and yeah, it was just kind of grinding through all the stuff, doing one module at a time, layering it in, making sure everything fit. It basically, it worked. You'd end up with some flexible wire, kind of excessive flexible wire, but there were places for it to go. My LEDs turned out to be too bright, but my wife had some nail polish, like costume nail polish. So I actually used it thinking that it would make part of the LED opaque, but it turned out that the LED would shine through it. So it created a very nice, like this one's blue, these blue and purple, and it created just the right amount of brightness. It actually worked out great. So I used white LEDs with nail polish. This is my cat protection every day. I tear it down, get some cat protection. This is making my own cables. So I would first tin the cable, and then I would touch an iron to the plug for like 10 seconds. And then I would push solder into the hole, like the hole and the wire here, and try to fill that hole with solder. So here's an example of one that's done. And I would use a 800-degree iron and a fat tip. That's the fattest tip I have. And when I did that, it worked pretty well. It was a bit challenging with a small tip. Here's some of the modifications I made. So here's the gated comparator with the DAC. So these three cables run to A, B, and C jacks and correspond to these positions on the DAC. So this is like a resistor ladder network DAC. And so this way, instead of these values being internal to the DAC, which you would achieve by jumpers, it's just directly connected to the front panel jack, so I can use whatever module I want to generate those signals. Here's an example of having to do something when I didn't use a pot that was specified on the front panel. So sometimes you can just ignore these, but sometimes and often when there is power supply like current running through the pot, um, the rest of the module expects there to be some voltage there. And this is where having schematics really helps. So in this case, I had to jumper this in order for things to work. Peak and trough, I use the same input jacks for both peak and for trough. I also used a 0 volt reference somewhere. Yeah, here you can see 0 volt, these green wires. So that it's basically doing like half-wave rectification if you only put one signal in to the peak and the trough. For the VCAs, I used push-pull pots. So at one point, close to the end, I decided that I had too many VCAs and not enough mixers. So I looked at the VCA circuit and decided that it can kind of be a VCA and a mixer. So basically that module, it has multiple inputs, audio inputs, and it basically sums those into a single signal. And that has multiple control voltage inputs, and it basically sums those into a single control voltage. And then it's a VCA with the sum signal and the sum control voltage. Well, I only had the panel layout to use one input and one control signal. So it occurred to me that if I made the panel jack for the control voltage switch to another one of the input signals, then in that mode, it would be a mixer. And then if I switched it back to being used as a control voltage, now it's used as a VCA. So this push-pull pot does that. When it's pushed in, it acts as a VCA, and when it's pulled out, it acts as a mixer. And really the only defect here is that on the panel, it's not obvious that it does this. I should have changed the panel lettering, but I had already finished the panel at this point. So this is what it looks like. So the wiper comes down, I think, to the center here of the switch. This is actually a dual pole, and I'm only using a single pole. And then I think the blue goes to the control voltage on the PCB, and the black goes to the second input on the PCB. And this is it acting in mixer mode. So you can see in mixer mode, it's kind of unity gain when the attenuator is turned all the way up. And this is it in VCA mode. In VCA mode, it's bigger than unity gain. So sorry, the blue is the audio, and the purple is the control voltage, and the yellow is the VCA output. And this is when there's no control voltage and no input. It looks like this. So basically, with this, the way I have it set, the VCA is always half on. So anytime you just plug something into it with no control, you're going to get half the signal. And I thought this might be useful in other ways. I just decided to leave it like this. I thought it's a little bit weird, but I feel like it's in some weird ways, it's actually more flexible than the standard VCA behavior of being fully closed. If I looked into it and I thought, well, if I want it to be fully closed, what I would do is I'd use the other side of that dual gang switch, and then I would put a trimmer here in P4, and then I'd have one leg go to the switch and the other leg come back, so that basically when it was in, I can't remember now, when it was in, I guess, mixer mode, that it would have this this offset, so that the VCA would be fully closed in VCA mode, and yeah, work appropriately, like work the way you would expect as a mixer and as a VCA. This is the headphone board, kind of just showing what it looks like. So you can see the headphone board, it's right below the output board of the mixer. I think I talked about this, but I originally thought I would go directly from the output board to the inputs of the mixer. Sorry, the output board directly to the inputs of the headphone board. But yeah, I think those pins are sitting right in front of a op amp. So instead, I went from the outputs. It seems to work. It seems to work fine the way that it does now. This is just the headphone. It's a dual gang pot. So I had a little bit of a funky adapter, a little bit different from the other ones I did, but not interesting enough to have lots of photos of. And yeah, and this is just the final. So basically, when I put in the final boards, everything was so tight at that point that I had like 5 hanging out, and I kind of put like all 5 in at once. So it's kind of interesting. All right, so this is it. All done, all the boards in, all the power wired up with these terminal blocks. Most of these cables, I think, are a good length. Some of the early ones I started with, I think I made a little bit too tight. I mean, you know, it still folds out and everything, but I don't know. The back bolts on, and there's nothing really capturing the nut for that bolting on. So I just use hot glue, and this was fine as a temporary thing, but I think if I come back in the future, I'll probably laser cut out some pieces of wood that have the shape of the nut cut out in them, and then glue the nut into that, and then glue that piece of wood onto this. So basically it captures the nut, prevents the nut from turning when a bolt is screwed in, and also keeps the nut from just like falling out when the bolt pushes into it a little bit. So I mean, this hot glue thing works, but I don't think I'm going to get very many cycles before it fails. So this is the back all closed up. This is the finished product. And then I originally was going to put it in this Apache case. I like these cases, but they taper towards the inside, and I ended up with the boat being steeper than I originally thought. And so the only way to fit these two in and get like 7U of space is for them to kind of be wedged together, which you can kind of see here. The Euro boat is elevated on one of, like on these, just as an example. Um, so they would have been right up on each other. They would have rubbed against each other. And at this point, I'd gotten a little bit precious about the boat, and I just didn't want that. I just didn't want the finish to get rubbed on and stuff. So I dug up an old case that was bigger and had the possibility of foam. And here you can see, some abused pull apart foam from a previous project. I used a mattress topper to do the top piece of foam and make it the correct height. And this actually works really well. I'm really happy with this. So problem solved. The Euro thing will be populated with other more complementary modules. Actually, I just made this out of scrap. So it looks pretty damn ugly. Maybe at some point in the future, I'll actually make one that looks nice. But yeah, this is literally scrap wood that I built other things out of that I broke down to make this. So so yeah, that's my last one. Yep. So yeah, just as a recap, if you've done DIY your rack before, I think it's totally reasonable to go get like DIY kits from Logain or Prism. Logain's got this Voice of Reason that looks very reasonable. Prism's got some stuff. You also can do not panels and just do like individual modules, which there's a lot of reasons that makes sense, right? They're probably easier to sell. You can reconfigure them later if you want, like you can rearrange them and stuff like that. You can also buy the stuff used. And of course you can buy like new stuff from Serge Modular. Use things like if it's been quote properly manufactured, they seem to be 2,000 to 3,000 in US dollars in 2025, 2026. If it's somebody's DIY project, you might be able to get them for down to like $1,000. So a lot of the DIY stuff doesn't seem to sell quite as well. I guess it just depends on if people trust you to have built it well. But to do the level of DIY that I did on this project is really a lot. I've got hundreds of hours in this. Yeah, but I learned a lot. So, just depends on what you want to do. Feel free to ask questions in the comments. If you found anything wrong, I said something stupid, or you want clarification, I'll put all sorts of clarifications in sticky at the top of the comments. All right, thanks.